Hello everyone, my name is Xuan. In this video, I will be demonstrating the use of HWiNFO64 as a hardware sensor monitoring tools to capture and analyze COA performance metric for both workload A and workload B as part of our computer organization and architecture group project. HWiNFO64 is a free and professional-grade hardware analysis and real-time monitoring tools for Windows operating system, and it passively monitors hundreds of hardware sensors simultaneously while an external tools generates the CPU stress. For this project, I pair HWiNFO64 with Signbench 2026 as the load generator. HWiNFO64 runs silently in the background in sensor-only mode and captures real-time data including CPU clock frequency, core temperatures, thermal throttling events, and power consumption, which are critical COA performance metrics. For workload A, I open HWiNFO64 and select sensors only mode for the startup dialogs. This opens the sensor monitoring panel directly without the additional system summary window. Next, I open Signbench 2026 and configure it for the multi-core workload. According to workload A specification, I set the render duration to 30 minutes using the file setting menu and select CPU multi-tricks mode. This continuously triggers a heavy rendering task across all CPU cores to simulate maximum pipeline saturation. Before I starting Signbench, I initiated a CSV data logging in HWiNFO64 by clicking the logging icon at the bottom toolbar. I save the log file and name it as workload A. This ensures all sensor readings are recorded every second throughout the entire benchmark run for post-analysis. With CSV logging active, I then start the Signbench 2006 multi-core benchmark. Here you can see both tools running simultaneously. Signbench is actively rendering the 3D scenes using all CPU cores, while HWiNFO64 is continuously updating all sensors value in real time. I am monitoring 4 key sensors group here. First, the core effective clocks. This show the actual CPU operating frequency in real time. Second, core thermal throttling. This show yes or no indicated for whether the CPU is being thermally throttled. Third, CPU package power, showing how many watts of CPU is consuming. And fourth, the core temperature section showing CPU temperature in degrees Celsius. After the benchmark complete, I stop the CSV logging and open the log file in Microsoft Excel for analysis. Here I can see thousands of rows time series data captures every seconds during the run. From the core clocks data, I identify the highest recorded clock frequency as 3162.3 MHz and the lowest is 1047 and 4 MHz. Calculating the clock frequency delta, which is difference between the highest and lowest clock, gives us 2140.9 MHz. This large data demonstrates the CPU dynamically scaling its frequency under varying thermal conditions. Looking at the core thermal throttling columns, the current value shows no meaning trolling was not sustained throughout the runs. However, the maximum column recorded a yes value, confirming the intermittent thermal trolling events did occur during peak alert. This is consistent with the CPU reaching a maximum temperature of 91 degrees Celsius, with the distance to TJ max dropping to just 9 degrees, meaning the CPU was operating extremely close to its maximum safe temperature limits of approximately 100 degrees Celsius. Finally, peak CPU package power consumption reached to 29.996 watts, approximately 30 watts, confirming the processor was operating near its thermal design power limit during the multi-core workload. This combination of near maximum power draw, near TJ max temperature, and the intermittent trolling events clearly demonstrate pipeline saturation behavior. For workload B, I reconfigure the monitoring to focus on individual CPU core temperatures and clock frequencies. This is because workload B targets an advanced architecture behaviors, specifically dynamic trace migration and localized thermal hotspots formation. For my processors, is using the Intel's hybrid architectures with 2 performance cores labeled P-Core 0 and P-Core 1 and 8 efficiency cores labeled E-Core 2 through E-Core 9. This hybrid design makes workload B particularly interesting because the Windows scheduler dynamically decides which core to assign a single threaded workload to. I configure Signbench 2006 to run in single core mode for approximately 10 minutes. Using single core modes, isolate the workload to one core at a time, making trace migration and thermal hotspot patterns clearly visible in HWiNFO64. With CSV logging started, I launched the SignBench single core benchmark. While it ran, I observed the individual core temperature readings in HWiNFO64 carefully. Notice how P core 0 and P core 1 temperature are significantly higher than the E cores. This is the thermal hotspot forming on the performance cores as they handle the demanding single threads rendering workload. After approximately 30 minutes, I stopped the benchmark and analyzed the CSV data, starting with core temperatures. P core 0 recorded the highest maximum temperature of 2 to core 7, or recorded a maximum of 80 degrees Celsius, while at core 9 and core 8 remain the coolest 68 degrees Celsius. This confirms that the single threads workload are concentrated on P cores, generating the localized thermal hotspot in the high performance core cluster. Looking at all the core clock frequency, both P core 0 and P core 1 recorded identical maximum core speed of 4,489 MHz, significantly exceeding the E core maximum of approximately 3,092 to 3,192 MHz. This confirms the P cores are the primary execution unit for demanding single thread tasks. The fact both P cores reach the same maximum clock frequency, but different maximum temperatures of 98 degrees versus 87 provides strong evidence of dynamic thread variation. The Windows scheduler initially assigned the workload to P core 0, which reached the highest thermal load of 94 degrees. To prevent substantial trolling, the scheduler then migrates the threads to P core 1, which recorded a lower peak temperatures of 87 degrees. This demonstrates Intel's Trace Director Technologies actively managing thermal density across the hybrid core architecture. To summarize the finding from both workload using HWiNFO64, for workload A, the multi-core stress test revealed that the processors exhibit significant Intel Turbo Boost behavior, boosting from its 2,500 MHz base clock up to 3,162.3 MHz under load. However, this performance comes at a thermal cost. The CPU approached 91 degrees Celsius and experienced intermittent thermal crawling events, causing clock frequencies to drop as low as 1,647.4 MHz. The clock frequency delta and near 30 watts power consumption clearly demonstrate pipeline saturation and thermal management under sustained multi-thread load. For workload B, the single core test exposed the thermal hotspot formation and thread migration behavior of hybrid architecture. P core 0 formed the primary thermal hotspot at 94 degrees Celsius, triggering the Windows scheduler to migrate the workload to P core 1. The E cores remains significantly cooler 68 to 80 degrees, confirming they handle only background tasks throughout the benchmark. HWiNFO64 proved to be an extremely effective monitoring tool for this project. Its ability to simultaneously capture hardware analysis in single CSV log file make post-run quantitative analysis very straightforward. Let's conclude my demonstration of HWiNFO64 for COA projects. Thank you for watching.